Hello, everybody. This is Chad Julius with Alan Block. I've been with Alan Block for 18 years and looking forward to this topic. Kind of hits close to home. I've got a geotechnical engineering background, and today we're going to continue our discussion with our Contractor ABU online and specifically the topic about dealing with poor soils. So with that, I'm just going to carry on and move through the presentation. You have the ability to ask questions along the way. I do have everybody in a listen-only mode, so you should be able to see and hear me at this point. But there are a couple objectives that I have for today. First, I want to identify what poor soils are and what properties exist with them. And then we want to develop an understanding of what some of the challenges are associated with these soils when you encounter them on a job site. And then obviously towards the end there, we're going to talk about ways you can handle and work around these poor soils as you still look for solutions on your job. So what are poor soils? I know through the webinars, I know my experience, a lot of people go with clays and stuff that's very saturated and a mossy peat and organics, and all those are relatively good answers. But really, when we define a poor soil, we're really looking at anything that does not compact or provide stability. When you look at this building here, obviously something happened to those soils, whether they collapsed or shrunk or they had some major issues. So really anything that does not provide that stability can constitute as a poor soil. Now there's properties and soil characteristics that can lead themselves to the poor soil classification, and we'll talk about that. And a lot of it has to do with that water content, whether it's too wet or if it's too dry. And so when we get into this, we want to talk about how do you identify poor soils, and that's really what the first topic is all about. And here's some major red flags when you're looking at these. Obviously, when you go to a job site and you see a visible standing water, obviously you're talking about just saturated conditions, and that could be very problematic and lead to soil properties that are going to be very, very hard to compact. Obviously, if the soil is very soft or if the soil has cracks, the cracking might represent that it's too dry, and again, it's going to limit itself to consolidation and compaction over time. So how do we know we have poor soils? You look at a picture like this, and in the segment of retaining wall industry, we see something like this on a daily basis. Everybody's excavating a cut and they're making room for their wall. And even though this looks like a reasonably good soil, we know that there could be problems. You should never see a vertical cut. A vertical cut means you've got some soil properties that are very cohesive, and cohesive soils can tend to lead to some problems because they're very sensitive for water. So, like I said, how do you know you have poor soils? I wouldn't say that this is a red flag, but you definitely know you've got cohesive soils, which means you've got some water sensitivity going on a soil conditions like this. So, there's some little things that you can look for. Obviously, we always say grab a handful of that soil, and I'll get more into this as we get to different classifications. But since clay seems to be what people center on, there's different states of clay, and we'll get into more of that when we actually do the testing. But if I grab that soil and I squeeze it, and it tends to hold the shape of that palm, we know we're talking with a cohesive soil, some fine aggregates there. Obviously, when it gets too wet, that picture down on the bottom, you're standing in mud, and that's kind of a liquefaction where it's behaving more like a water than it is the soil, and there's no way you're going to get stability with something like that. But then even on the flip side, on the picture on the right, when it's too dry, obviously if you're excavating into a clay material and it just flakes off or chips off, there's really no way you're going to get it to recompact to where you need it to be and provide that stability unless you get to that water content again. So again, that moisture, we're going to come back to that quite a bit here today. That moisture is so important. But let's talk about just classifying the soils before we get into the clay here a little bit more. We know that if we grab that sample of soil and we can ball it up, we probably do have that cohesive soil, as we've talked about before. But if I take that sample of soil and then I try to squeeze and it doesn't really stick together, you're probably looking more of a granular material. And that can actually be advantageous when we're talking about retaining walls. And then if I grab that sample of soil and it's maybe a little bit more dark in nature, black in color, but it will stick together, but really not hold. It doesn't really have any stability properties. We're probably talking about organic material. And really, when it comes to retaining walls, we know when we're building in clay, that clay will put additional pressure on a wall, and that's all important. But it probably will require some additional engineering and maybe some reinforcement when it comes into that. Sands and gravels, we'll get into why that's great, a little less sensitive to the moisture because it will drain and consolidate a little easier. And then we've got the organic materials. Obviously, the big red flag for organic material, we never use that in wall construction or really any kind of retaining wall construction for that matter. Great for restoration activities. We can go ahead and stockpile that material and bring it back onto the top couple inches or millimeters of your wall for growing things, but we never use it for wall stability. So classifying soils, really what it boils down to is we got to check the size of the particles, the different ranges of conditions. We know there's different strengths along the way as well. We call those friction angles, and we'll get into kind of a common sense approach of determining what those look like. And then kind of classifying the different types of clay. I'm going to talk about the Atterberg limits just so you get a better appreciation of what we're looking for there. So when you talk about particle size, this has been the time-tested and true method of just determining how big the soil particles are. This is a sieve analysis, and as you work down that column of sieves, the openings of the screens will slowly get smaller. And so the top sieve will have a larger openings, and it'll go all the way down until we basically collect it on what we call the pan down below. And you just shake the soil on there and then let it work its way through. So this is just a particle size distribution curve, and you really don't have to pay attention to the curve itself. Really what I want to point out is anytime you're plotting your results, you're really looking at how much is being collected on the individual sizes. So right there across the top, we got boulders and cobbles being reported, and that's really anything over 3 inches or about 70 millimeters. We get into the sand, the gravel, you've got the coarse, medium, and fine, and that'll go anywhere from an inch and a half or 3 inches down to what we call a number 8 sieve. And really what that is for us in the States, that means you got 8 openings per 1 square inch. So you can see that it's getting smaller. Then you get down into the sand particles, that goes down all the way down to a number 200 sieve. And that's where we identify between a sand and those silts and clays is that 200. So anything passing that 200 sieve is what we call a fine aggregate or fine grain material. And then now we have to do additional tests because then it is determined by, the plasticity of that. So really important to identify the size of the particles. And the only way to really do that is kind of do that sieve analysis to determine how big those are. And you can see we go from all the way from boulders and cobbles all the way down to those silts and sands. We get into the friction angle or the strength of the soil. The geotechnical engineering community will grab a sample of that soil and they'll run what we call shear tests on those. And that's the only true tested way that you can get what we call the friction angle, which is that strength of soil. But anybody can do this experiment. You can take a bucket of sands and gravels and dump it out right next to a bucket of clay material, and you'll notice that because of the clay particles, they'll slough off a little bit more. That pile will be a little bit wider, it won't be as tall. Where if you're talking about sands and gravels, it'll cone up a little bit higher. What you're witnessing is that natural strength of soil. So it's so important to classify or determine what type of material you have on a job site. Because if I simply just look at what that soil does to a retaining wall, you'll see it's pretty obvious. If I've got clay material, everything below that line is technically stable. It's stacking on itself. So this wedge of soil that's above this line is what's putting pressure on my wall. So you can see sands and gravels is a much stronger material, so that wedge is smaller. So if that wedge is smaller, now I've got less soil that I'm retaining, and it puts less pressure on the wall. So there's many reasons why we like that sand and gravel as that backfill, because it handles that water better and it puts less pressure on that wall. So there's a reason why we classify that. But now we get into the clays, and really when it boils down to the clay material, it's talking about how expansive that clay can be. What is that potential? And we talk about that as like a plasticity index. And really what you're trying to do is determine at what levels does the clay start to behave differently. And we've got different tests, the liquid limit test or the plastic limit test. There's different ways to test that in the lab. But really what we're doing is we're taking that hard clay, and we know it's kind of a solid, but as we add water, so if we continue to add water coming through here, it's going to start behaving less as that solid and a little bit more like a liquid. And so as we transfer to that plastic, we got that plastic limit. And that's that PL that's labeled there. And then as we continue to add water, it'll behave a little bit less as that moldable material and a little bit more like the liquid. That's that liquid limit. That's that threshold that we're looking for. So the plasticity index is simply nothing more than the difference between those two moisture contents. So for us in our industry, we start looking at plasticity indexes greater than 50. That means you're dealing with a very fat or heavy clay. And all that means is you've got a clay material that is going to be very, very expansive. It's got those properties that when water is introduced, it's going to expand and cause problems behind that retaining wall. And we see it all the time. Anytime you're building in expansive clays, it may look okay, but then as water is introduced, it'll just start creating that additional pressure. Not so much hydrostatic pressure per se, but soil pressure because it expands. So for that reason, we know there's some allowable materials that can be used, and you can see the allowable, we have a liquid limit less than 40, but a plasticity index less than 20. And so we definitely want to make sure we've got something that's not going to expand. Now, in our industry, we've got what we call best practices. And best practices is our initiative for zero wall failures. And so obviously when we're talking best practices, recommendations even get a little bit tighter. So we really like a liquid limit less than 30 and a plasticity index less than 10 when you're talking about best practices. And so it really gets down to understanding what type of clay you're dealing with, because I always like to tell everybody clays are not created equal. You can say, yeah, you don't have a sand and you can assume a clay, but we've all been part of projects where clay material might be heavily expansive or clay material might have a friction or a strength that is next to nothing. So that's where these tests really come into play. And that's where the classification comes in. I know we've got some partners from overseas and there's different classification systems, but they're all based kind of on the same thing. You've got particle sizes, you've got the Atterberg limits or different classifications of clay. In the States, we tend to use the Unified Soil Classification System, or the USCS. And really what I want you to do is just kind of look at how we're classifying these soils, and it really boils down to what we've just discussed. So we start with the gravels on top, and then we get down into the sands, and those are just giving a symbol of either a G or an S, because that's the prominent particle size. But then you get into different characteristics, whether it's well graded or poorly graded, or you got a little silts or clay particles to it. The well-graded sand or poorly graded sand. Poorly graded sands are more of like your beach sand or a sugar sand. We kind of refer to it when you're not on the beach, but there means it's all the same size. And so like a beach sand they're all the same size, but it's still a sand, but it's just poorly graded. Then obviously silt and clay particles. What I want to just point out the attention to here a little bit is the clays. We got that liquid limit, less than 50, greater than 50, and that is the difference between your lean clay or a fat or heavy clay. And obviously, when you're talking about clays, if it's more of that lean nature, under 50, those can be suitable for construction activities. Anytime you're getting into a liquid limit or higher than 50 and you've got that fat, heavy clay, we're looking at material that's probably going to have to be fixed or removed from that job site. But I keep talking about clays, but they're not the only problem soil out there. When we talk about, in general, I classified poor soils as anything that cannot be compacted or really add that stability. And one of the things that often gets overlooked is a lot of people like to bring in some cobbles or some bigger material, and that's very difficult. It's not easy to recompact that or make sure that doesn't shift through consolidation. So, if you've got larger sizes, especially anything larger than about 2 inches, we're probably going to need to use something that's got smaller diameter. But then those poorly graded sands, like that beach sand or sugar sand I was describing earlier, those can create those own problems as well. I have no problem with that poorly graded sand being used for the most part, but we know there's some additional design and construction steps that are going to be required. We know that the water can penetrate and flow through that sand, but it can actually move that sand a little bit. So on the design side, what we do is we just encapsulate that material with a geotextile or a fabric, so that way that will stay in place and perform just like we want it to. So anytime we're dealing with poorly graded sands, we're generally recommending some type of a fabric to encapsulate that, which is one of the few times we do recommend fabric vertically behind a wall. Normally we're just talking about the geotextiles horizontally. And then I've already mentioned a little bit about those organic soils. Obviously, anything with organics in it could decompose over the lifetime. And so anytime they decompose, they're going to settle, which is why anytime there's excavation activities, we're always looking for those organic soils and removing those and replacing as we go. So I keep coming back to compaction and stability because to me they are one and the same. When you're talking about soil characteristics, we know we need to have compacted material if we're going to minimize the settlement characteristics. So to do that, we know that there is a moisture content that's got to be obtained. When you're building a sandcastle or built a sandcastle with your kids, what you're doing with the sand is you're adding a little water to it to help get it to stick together. But then over time, if you add a little bit too much water, the sand's just going to run away. So there's that sweet spot for that sand. And then obviously, when it comes to compaction, it's the level of effort. It's the loading that's being applied to it. So using the right compactor is important too. So I brought this into just because I think it's important. It's really kind of that compaction curve. So we've got the water moisture being increased as we go left to right, and the density increasing as we go up and down. So this curve is perfect, right? So as we add water, that density goes up, just like that sandcastle I was talking about before. But you get to the point, that peak curve there, where all of a sudden you've reached those optimum conditions. So adding any more water to it is only going to hurt you, and your density actually goes down. And that's what that compaction curve provides. It gives you the optimum conditions for any particular soil. You can run a compaction curve on a lot of the backfill material out there for you. But then it gets into the type of material that we're using for compaction, type of equipment, and I always say choose wisely because they're not all created equal. I know a lot of contractors, they tend to just drive back and forth with their equipment, and that's not going to get the compaction they need. You actually need compaction rated equipment, and that vibratory plate compactor that you see right here on the left-hand side is great. It is great for that granular material. We love it in and around the wall, the block itself. So on top of the block, behind the block, it helps consolidate the rock that's in and around that zone. But when you're talking about fine grained material like your clays and silts, that's where those rollers really come into play. You might have to put a little vibration to it, but when you're talking about clays, we actually like to kind of roll it through and kind of knead it together, so you're removing some of those air pockets in there too. So great piece of equipment when you're talking about those fine aggregate or fine grained materials and cohesive soils. Then on the right-hand side, we've got that little jumping jack, I always call them. Great compaction piece of equipment, don't get me wrong, but let's face it, we're trying to keep the block pretty level. And so you might be able to use something like this in the foundation area, but behind the block, it gets to be a little bit problematic because they're pretty violent and you lose control of that a little bit, and all of a sudden you're moving the block. So we tend to not use those or recommend those for compaction activities behind the block for that reason. So we talked about soil characteristics and why it's so important, and what kind of problems that are associated with that, because anytime they swell. Let's talk about some of the fixes. All right, and this is just not an end-all be-all list, but it covers the basics, right? And so we've got 3 different options that I'm presenting here. We got remove and replace, we got a soil correction option, and then we got what we've done from time to time, kind of a pre-wetting or drying, which is really kind of controlling that moisture content. But let's get into the most common. Obviously, it is the most common way we handle poor soil, especially when you're talking residential applications. If you see organic soils, what do? You remove them. If you've got a soft clay and it's in your foundation, what do? You over excavate and bring in more rock. If you've got very poor soils behind the wall, you're always removing and replacing. Like I said, in our industry, especially on the residential side, this is the go-to solution. And what we love to see is we're starting to see more and more of our contractors out there from coast to coast and around the world starting to use more of that clean stone. We call it wall rock for that backfill. They've recognized that, yes, I might have a little bit more cost in the material, but it speeds up their installation. It consolidates faster, compacts faster, it builds a better wall. So it really kind of supports the best practices too. So remove and replace is right in the wheelhouse, as I always say, right down the alley when it comes to segmental retaining walls, and really, for obvious reasons, our go-to solution. But that might not be the only solution, especially when you're doing larger projects. If you've got a large commercial site and you've got some questionable soils there, you might be money ahead by getting a geotechnical engineer involved and letting them look at the soil characteristics, and maybe there's an additive that can be applied to the soil. So now the moisture content isn't as sensitive, or maybe it brings it into a workable material. And guys have used even like a dry sand, but I've seen them use lime, even some silica fume fly ash, or even some polymers that have been used. But what you're doing is you're adding that to the soil, and then you're using that as backfill material. And if you can use the on-site soils and you don't have to ship them off and dispose of them, then you're money ahead. So we tend to see these a little bit more on your larger projects. That way these guys are saving a little bit of money over the time. But you got to get the professionals involved, because this isn't something you're just kind of shooting from the hip. You got to understand what's going on. And that holds true for the next solution too. We call it pre-wetting. Really, I see it more done in our foundation soils, not so much behind the wall. But if you're excavating and you got your trench cut and you've got some expansive materials or potentially expansive materials there, we pre-wet them. So what we do is we add a little water to it, get it closer to its optimum condition, maybe even a little bit past, but you just get a little bit to that optimum condition. So you're expanding that material already. So that way, when additional water gets added or anything like that, it's not going to expand. I always look at heavy fat clays or that expansion clays as kind of like that sponge. As you add water to it, it'll continue to move up. And what we want to do is kind of control any future movement. So if we expand it before the construction activities happen, then we can minimize the swelling and hopefully the shrinkage over time. And that holds true when you've got drying the material out, especially if you got soil particles that will tend to collapse when the voids are free and you've got open pockets there. And so making sure you're reaching those optimum conditions before you even start compaction. And that native material is so important to understand. So it really gets down to water management. I know you guys have attended our Contractor ABU online sessions in the past, and we tend to overemphasize the importance of water management, but I don't know how we cannot. It is the key element for everything we do, because once a wall is built, the assumption is going to stand up forever. So something's got to change if there's going to be potential problems, and more often than not, that change has to do with that water source. And so we know future water, or maintaining that water management, is the key if we're going to keep that soil performance in the future. And so it gets down to two sources. We got the surface water, we got the groundwater. Surface water to me is the obvious one, but even the one that is probably neglected the most. On residential applications, a lot of the culprit is the downspouts. Where is that water being dumped? And if it's going right behind the wall, now that's going to change your soil characteristics. You're introducing additional water, and now you're past your density curve, your compaction curve already. So we're looking at this, berms, swales, get that water out and around so it doesn't even have a chance to hit the back of the block and start saturating those soils. So this is where you need to be proactive, making sure these surface water potential sources are handled. But even the groundwater, that's your secondary source. You look at that, all we're trying to do is provide that path of least resistance. So if a water source is identified, whether that's a fluctuating water table that might come from the bottom up, or even a natural spring or something from the backside. All we're doing, as you can see here, we're just adding additional rock. We're just bringing in something that is going to capture the water, whether it's at the blanket drain or a chimney drain here. We're just going to grab that water, get it out from behind the wall so it doesn't even have a chance to alter the performance of the soil characteristics. And that's the key. Water is the biggest thing we got to look at, but other design considerations, especially when you're talking about poor soils, more often than not, you're probably going to have to lengthen grid. You're going to need more reinforcement because the poor soils will put additional pressure on that wall, or maybe that's that questionable settlement activity that we're going to have. So we need something that's going to be able to account for that additional pressure. Without a doubt, if you've got poor soils, you're going to have to tighten the compaction specifications. Our recommendations is to backfill compact every course, which is, if you think about it, that's an 8-inch lift. Depending on your soil conditions and the compaction equipment on the site, there's no way you're going to be able to do an 8-inch lift. So really, you're going to have to tighten that up. It's not unheard of to even cut that in half or even a quarter. I know some guys that have had to use almost a 2-inch lift to get that compaction done and meet the compaction requirements that we're looking for. And then obviously, we can't build on junk. So if you're excavating and you see some soft soils, getting kind of a page out of that remove and replace is to oversize your footing. Dig it a little deeper, dig it a little wider, even introduce some geogrid reinforcement to help you bridge over some of that questionable soil and even minimize some differential settlement. So design considerations are water management, what is the reinforcement requirements, and then making sure you've got suitable material below the wall and tightening up those compactions. So, but that's really what I wanted to kind of highlight. The Contractor ABU onlines are meant to be short, brief, to the point. Our whole goal was to identify poor soil properties. We talked about clay materials. We talked about that differencing. If you got a heavy fat clay, that's going to put more pressure and shouldn't be used in construction at all. But we also talked about poorly graded sands and even organic material. Understanding some of those challenges when you've got poor soils at your site. And then we even discussed a few of the simple solutions. Obviously, I keep coming back to removing and replace, but that is kind of the go-to solution as we go through this. But what I want to do is encourage you. We get to do retaining walls every day. Our production partners out there get to do retaining walls every day, and so use that. As a contractor, you get pulled in a lot of different directions. So we want you to use the resources you have available to you and reach out to not only Allen Block Corporate, but your local contacts there, and let us know how we can help. And so with that, what I'm going to do is just kind of pause here, let you guys ask any questions if you have them. I've been kind of looking at that question box here, and I haven't had anybody type anything in yet, but if you do have any questions or comments, feel free to add those now. But as you guys are working on that, I just want to, again, thank you for your time. I know it is a busy time of the year right now, and people are trying to finish up projects in some markets and get started in others. But we also know doing this the right way is so important. So taking a little time, getting educated on dealing with poor soils is so important. So didn't have any questions, did have a couple thanks, so I appreciate the words of encouragement there. Without any questions, I'm going to let you guys carry on your day, and I'll close out the webinar here and look forward to helping you on your next project. Thank you so much.